Can anyone see my screen?
Yes, but you're speaking very softly, or your microphone is not working so well on my end at least.
Can you hear me now? Is it
Perfect.
better? Okay.
Yes, much better.
Great. Thank you. Hello, everyone. So we are here for the new seminar series of the IGAC Early Career. So our goal is to actually offer the opportunity to all ECRs to present what are they doing and to discuss with peers. So in case you would like to participate on next editions, we have the link on the chat. So please make sure to nominate yourself or a colleague, well, with their consent, of course. So essentially, the idea is that we are going to have a series of seminars like this. And also, if you don't do it yet, you can join our newsletter and then get to know what is happening around. So also the link is in the chat. We are going to have today two presentations. The first one is gonna be with Damaris Tan. She's from the UK Centre of Ecology for Ecology and Hydrology and University of Edinburgh. She will talk to us about biomass burning today. And then right after the talk, we're going to have a break for questions and discussion. And we'll have a second talk. And then I can present afterwards. So if you have any questions, please put in the chat, or right after the presentation, you can ask directly. Okay? Well, let's have a nice seminar. I'll stop sharing now, and then Damaris can share the screen.
Okay, let me just make that full screen. Is this working okay still? Yes. Perfect. So thank you very much for the introduction, and thanks for giving me the opportunity to present here today. And thank you to everyone who has tuned in. My name is Damaris, and I'm a PhD student at the UK Centre for Ecology and Hydrology, and also the University of Edinburgh. I'm supervised by Matt Heel, Aiko Nemitz, Massimo Biano, Stefan Rice, and David Stevenson. And yeah, today I wanted to present a little bit about my work looking at open biomass burning emissions, particularly some unexpected consequences for surface ammonium nitrate formation. And as the title suggests, this is very much about open biomass burning emissions, but it's also about sort of the more conventional anthropogenic emissions and really about the interaction between these two. But more on that later. Let me first of all start with the definition. Here I am defining biomass burning as wildfires, prescribed fires, and agricultural fires. And these have many impacts on the environment, including impacts on air quality. Particularly, I am interested in fine particulate matter, which has a big influence on poor air quality. And just to give you a number here, in 2019, there was an estimated 4.2 million premature deaths due to sort of the total fine particulate matter. So it is important, and it is something we need to worry about. So the question is, how does biomass burning impact air quality, particularly fine particulate matter? So we know that biomass burning emits a lot of primary fine particulate matter, which has human health impacts. And it also emits a bunch of trace gases, which through a variety of atmospheric processes leads to the formation of secondary fine particulate matter, which also has these human health impacts. And this secondary fine particulate matter is what I am interested in, particularly ammonium nitrate, which is a major component. So moving on to my methodology, I am using the EMAP MSc West atmospheric chemistry transport model, and I am simulating the year of 2019 on a global scale at 1 by 1 degrees resolution. I'm using meteorology from WRF and HTAP version 2 anthropogenic emissions and the latest FIN version 2.5 dataset for the biomass burning emissions. And I did the usual model runs. I did a base run with everything switched on, and I did a no fire run, which I called NOF, which is with all the biomass burning switched off. And if I subtract the two, then this is going to give me an estimate of the change associated with biomass burning, or the impact due to biomass burning. I have done some model evaluation. I don't want to dwell on this too much, but I'm just going to show you my comparison to carbon monoxide and NOx measurements. You'll see later why I chose these. But on the left, I have my NOx comparison to observation. I've used UK sites and I'm comparing annual means. So on the y-axis, I have my modeled results. On the x-axis, I have the measured results. And this solid black line is the one-to-one line. And as you can see, the model isn't doing too badly. It does seem to underestimate a bit compared to observation, but on the whole, it doesn't do too badly. Now, on my right is the carbon monoxide comparison to observation. So here I'm using surface flask measurements gathered with the NOAA campaign, and these are from sites across the globe. And again, on the y-axis, I have my modeled result. On the x-axis, I have the measured result. And a bit confusingly this time, the dotted gray line is the one-to-one line. But essentially, again, the model doesn't do too badly. It actually reproduces the day-to-day variations very well, but it does overestimate a little bit in this case. Okay, now, if I could move, yeah, there we go. So moving on to my results, I am going to show you some 2019 annual mean surface concentrations, all of which I have calculated by subtracting the no fire run from the base model run. And this first figure here is the total fine particulate matter associated with biomass burning. So this is both primary and secondary. And don't worry too much about sort of the numbers and the rectangles. The numbers are the spatial average over the rectangle. But the main point here is that we have hotspots over regions with a lot of fire activity. So for example, over Central Africa and over Southeast Asia and so on. So this is as expected. But if we contrast this to the ammonium nitrate component, which I have plotted on the right as a percentage of this figure on the left, we immediately notice that we have a very different distribution. So we have hotspots over regions which aren't typically associated with biomass burning, for example, over Europe or Eastern China. And well, I suppose now my rectangles hopefully make a bit more sense. So I've drawn these rectangles over my 4 key regions where I have noticed a very large percentage of ammonium nitrate. So over Europe, we have 48% ammonium nitrate, and over Eastern China, we have 44% ammonium nitrate. So a significant percentage. Someone always asks for the absolute values, so here they are. And so over Europe, we have 0.65 micrograms per meter cubed, and over Eastern China, 1.2 micrograms per meter cubed. And these are, of course, very low values compared to sort of the total fine particulate matter concentration. But if we contrast this to the WHO guideline value for fine particulate matter, which is 5 micrograms per meter cubed, this is when sort of these smaller contributions do become important. But the main point here is a very different distribution for ammonium nitrate compared to the fine particulate matter associated with biomass burning. And sort of that's the question I want to answer. Why is this distribution so different? And I thought the best way to try and do this would be to summarize what I think is going on And then once I've done that, I'll sort of go into the details and really try and convince you that this is indeed what is going on in my model. So I have identified 3 factors which I think are important here. First of all, we need the long-range transport of biomass burning emissions, particularly carbon monoxide and NOx. And these act to increase the oxidative capacity of the atmosphere, sort of across the globe. Then secondly, we also need a lot of local anthropogenic NOx emissions. So we need a lot of industry, a lot of transport. And in the presence of this local anthropogenic NOx, we get oxidation to HNO3. And then thirdly, we also need a lot of local anthropogenic ammonia emissions, so areas with a lot of agriculture. And then this reacts with the HNO3 from the previous step to form ammonium nitrate. So this is what I meant at the beginning. It's really about the interaction between the biomass burning emissions and the more localized anthropogenic emissions. And in areas where we have all these 3 factors combining, this is where it is likely that we see these hotspots that I have on the right. So this is all very nice, but let me now try and go into the details and convince you that this is really what's going on, at least in my model. So my first point was we need the long-range transport of biomass burning emissions, particularly carbon monoxide and NOx. Carbon monoxide has a reasonably long lifetime of a few months, so that can be transported long distances and it's well mixed. And the NOx can be transported as reservoir species, for example, as PAN. And these are both, the carbon monoxide and the NOx are both involved in the Hox cycle, which I have here on the left. It's just taken from the Jacob textbook, and I have the Hox cycle in red. And as you can see, if we add NOx to the system, then we get conversion of HO2 to OH. And we get the competing effect if we add carbon monoxide to the system. So we get conversion of OH to HO2. And the question is, if we add both carbon monoxide and NOx from biomass burning into the system, what happens? Well, here I have plotted the total Hox, the total change in Hox attributed to biomass burning. And we can see that we have positive values across the globe, which means we're getting a net increase in Hox due to biomass burning. So we're getting an increase in the oxidative capacity of the atmosphere. Okay, now moving on to my second point, I also said that we need local anthropogenic NOx emissions. And these are oxidized through the increase in Hox from the previous step. And on the left-hand side, I have plotted the change in NOx attributed to biomass burning. And we have sort of 2 opposing things going on here. First of all, we have a positive change in NOx over regions with a lot of biomass burning. So again, over Central Africa, Southeast Asia, South America, and so on. And then we have, so that's just, this increase in NOx is just direct NOx emissions from the biomass burning. We have the sort of the opposite effect over my 4 regions with a lot of, a high percentage of the ammonium nitrate, so my hotspot regions. So we're having a negative change in NOx over these regions. So we're getting the removal of anthropogenic NOx, and this is why we're getting a reduction. Ultimately, this forms HNO3, and I've plotted the change in HNO3 on the right here, and we do indeed have a positive change pretty much everywhere. Okay, and finally, my third point was we also need local anthropogenic ammonia emissions. And this ammonia reacts with the HNO3 from the previous step to form ammonium nitrate. And here I have plotted the change in ammonia attributed to biomass burning. And this is a pretty similar story to the change in NOx. Over regions with a lot of biomass burning, we have a positive change in ammonia because we're directly emitting biomass burning. And we're directly emitting ammonia from the biomass burning. But over my hotspot regions, at least over Europe and over Eastern China, we're having a negative change in ammonia because anthropogenic ammonia is being used up. when we add biomass burning into the system. This is a little bit less clear over India and over the eastern US, and this I think is just because the sort of reduction in anthropogenic ammonia is being masked by the increase in ammonia directly from biomass burning, but I do think that the mechanism is the same. And all of this leads to the formation of ammonium nitrate, and this is just the figure that you've seen before. So hopefully that was somewhat convincing. Of course, all of this comes with a lot of caveats, as does everything. So of course, all the biomass burning components that I have been showing you are very difficult to validate with measurements. All I can really do is validate the model output as a whole. And if that's sensible, then hopefully the biomass burning component is also sensible. And secondly, the exact numbers I've been quoting are very sensitive to many factors. For example, of course, the biomass burning emissions data set, particularly the NOx to carbon monoxide ratio. And the numbers are also sensitive to the atmospheric lifetimes within the model, and also the anthropogenic emissions and the meteorology and so on. However, very reassuringly, the chemistry stays the same. So I've done a lot of sensitivity experiments to see what happens if I change the biomass burning emissions, what happens if I change the anthropogenic emissions. And while the numbers change, the chemistry always stays the same. And then finally, I'm only looking at 1 year. I'm looking at 2019, which was a very typical year for biomass burning emissions. So if we see something happen in 2019, then we're likely to also see that in other years. Okay, so I just wanted to finish off by summarizing. So I simulated the year of 2019 globally using the EMIP MSc West atmospheric chemistry transport model, and I calculated the impact of biomass burning on fine particulate matter. And I noticed that the distribution of the total fine particulate matter attributed to biomass burning was very different from the spatial distribution of just the ammonium nitrate component. And I noticed that there were high percentages of ammonium nitrate in areas with little biomass burning, for example, over Europe and Eastern China, where there was almost 50% ammonium nitrate. And I sort of put this down to 3 key factors. Firstly, we need the long-range transport of biomass burning emissions, particularly carbon monoxide and NOx, and these perturb the Hox cycle, leading to an increase in the oxidative capacity of the atmosphere. Then secondly, we also need local anthropogenic NOx emissions. And thirdly, we also need local anthropogenic ammonia emissions. And if we have the interaction between these biomass burning emissions and these more localized anthropogenic emissions, then this is what leads to this unexpected distribution of ammonium nitrate. I just wanted to highlight that this mechanism becomes increasingly important as nations aim to implement more stringent air quality guidelines, so the relative importance of these smaller contributions is going to increase. And then finally, I think this is very much a global issue. So if we want to get the chemistry right, then we do need to look at biomass burning on sort of a global level, rather than just looking at individual regions. And with that, thank you very much for listening. And I'll be happy to try and answer any questions. Thank you.
Thank you, Damaris, for a very interesting talk. If anybody has questions, please feel free to raise your hand or put them in the chat. I don't know whether Max or Emily was first, so you can, okay, Max, you're up in the corner, so you're probably first, so you start.
Cool, thank you. Thanks a lot, Damaris. It was really a tremendous presentation, and as somebody who also studies fire, very great interest in what you presented. I probably have too many questions, but I'm gonna try ask an easy one, but that would be interesting for me to learn is why did you pick Finn out of all the inventories?
That's a good question. The easy answer is that's sort of the default data set for my model. The model is, I think, if you put more work into it, it is compatible with GFAS as well and other ones. But yeah, And also, I think it was just exciting because the new Fin version 2.5 data set came out very recently, and it was sort of, I know a new fire data set doesn't always mean a better data set, but yeah, it was exciting to sort of use that one. And also, because I'm also interested in the UK, because that's where I'm located, the Fin data set has fire detections, I think, up to 375 meters resolution, something like that. So pretty well resolved. And that's important for the UK because our fires are considerably smaller than other people's fires. So when I do go on to look at the UK in more detail, then that will come in very useful. So my short answer and my long answer.
Cool. Thank you.
Thank you.
Emily, do you still have a question?
Do. Thank you for a really great talk. I was wondering, when you were trying to sort of understand the reasons for your different hotspots, whether you also looked at like the distribution of sulfuric acid around the globe, as that's going to be sort of quite an important sink for your ammonia, and so it'd be less than you interact with your nitric acid.
Yeah, good question. I did look at sort of the ammonium sulfate distribution as well. And I noticed that at least in my model and with this data set that the ammonium sulfate component wasn't quite as important as the ammonium nitrate component. I'd need to investigate a bit more to exactly find out why. It might just be the data set, or it could be because sulfur emissions have reduced quite significantly, at least in many parts of the globe. That might also be a reason. But yeah, good question. And I will definitely be looking at that when I take a more detailed look at the composition.
Thank you.
Are there any other questions?
I have a quick question. Damaris, you said that 2019 was a very typical year. Have you tried already like the extremes? A year that didn't had a lot of emissions and a year with a lot of fires?
Good question. I tried it with the old Fin version 1.5 data set, but I didn't look into it in a huge amount of detail just to make sure that 2019 was quite a typical year. And I also looked at it from more of a UK perspective. So in detail, no, I haven't. But I think that is probably a good thing to take a look at.
Max, I'm sure you have more questions based on what you said before, so feel free to ask another one if nobody else has any questions.
This is more maybe of a comment or discussion, but at the beginning you showed that your model has fairly good agreement with the NOAA CO flask, and that was because of the 1.1 sort of correlation factor. But you had a bit of a spread, and those flasks are taken at the ground, whereas a lot of the CO emission from fires is probably going to be lofted up in the air. And so this could be quite a lot of work. So obviously it might be tricky to fit that within a PhD study, but maybe comparing against MOPIT or Tropomi CO products,
Yeah,
which would
definitely
take the entire column rather than just the ground, which, it's tricky. I don't know if that's something that's out of scope or not.
I have definitely considered it because, as you say, it's important to see how carbon monoxide does sort of across the troposphere at least. I haven't done that yet. I think my model in particular, I'm told, doesn't do too well when compared with, especially as it's just a tropospheric model. But yeah, I think it would be worth maybe looking at some satellite data as well. Yeah. But since I'm mainly concerned with surface measurements, because it's really, for me, about the air quality close to the surface, that's why I sort of started with the flask measurements.
Nice, cool.
Okay. If there are no further questions from the audience, then I think we move on to the second talk of the day. Thank you, Damaris, for a great talk and
Thank you.
great discussion.
So our next talk is Dr. Pallavi. He's gonna talk. He's gonna share with us a little bit about air quality, climate change, and public health in India. Would you like to share your screen?
Yeah, I'll just do, and I might have to put off my video while I'm presenting to
No problem.
so that my audio is better. Yeah.
Okay. Yes, no problem at all.
Is my screen visible?
Yes. Yes.
Should I start?
Please.
Yeah.
Yes, that's perfect.
So greetings of the day, everyone, and thanks for joining, and thanks for this opportunity to present my work today as part of this series. And I'm going to present not just one study particularly, but an overview of the work I'm doing in this area, which is air quality and climate change impact on public health. While I had put in my abstract for the conference, where I have been like probably nominated out of that list. So that time I was a postdoctoral scientist at Indian Institute of Technology, Delhi. But in the meantime, I've now graduated to becoming an assistant professor in the Department of Public Health at a university in NCR near Delhi. So I'm now an assistant professor of public health, and my area of research is mainly environmental health and occupational health. So yeah, a bit about myself. Yeah. So I'm currently teaching, as I said, and my interest in environmental and occupational health developed during my PhD work, which I did from the Jawaharlal Nehru University in New Delhi. And that was more of health risks due to occupational hazards. And then in my postdoc term at IIT, I moved on to do a lot of work in the area of air quality and climate change stressors, how they impact human health. So I was part of a few projects related to mortality burden estimation of specifically PM 2.5 in Delhi NCR, which is one of the hotspots across the world, with one of the most with highest PM 2.5 levels in few months that we have here in Delhi. And then I was also part of the core team in Indo-Gangetic Plain air quality modeling project, which was funded by the World Bank. And then I also contributed in the health and climate co-benefits of air pollution management project funded by the Clean Air Fund UK. And more recently, I've also joined the Akash project, which is about actually the CRB burden and its impact on North India. And I'm a collaborative researcher with the Akash project, which is based out of the Research Institute of Humanity and Nature, Japan. And just to give you an overview, my research interest and my future research is mainly in three areas, which is creating policy suggestive evidence of climate change and air pollution stressors on cause-specific or all-cause morbidity and mortality, and also identifying sectoral health burden estimates to suggest the low-hanging fruits for mitigation, and also a bit about identification of vulnerable regions and populations in terms of environmental health impact. So probably what the broad term is environmental justice. Just an integrated workflow of what I do. So air pollution and climate change are two sides of the same coin, we could say, and both affect each other. And if we invest in mitigating air pollution, we are also in a way collaterally also having an impact on climate change mitigation. So they are both interconnected, and also their health impacts are interconnected. So interventions in one would also lead to co-benefits in mitigation of the other's effect on human population, right? And what my work is basically is upon air pollution, its short and long-term health impact. In air pollution particularly, I deal with PM 2.5 and PM 2.5 species, and then some multiple air pollutants also, like NOx, ozone and its impact, and also AQI, which is the air quality index, in terms of an index created out of multiple air pollutants. And then I also, apart from air pollutants specifically, I also work on climate stressors like heat wave days, days above 90th percentile temperature in a year, heat stress, which is not just heat, but combined effect of relative humidity, solar radiation, wind speed, and how exactly the temperatures is felt by human body. So it's short and long-term impact on multiple health outcomes. I work on a range of health outcomes. I'll just give an overview of what I have done so far and what is in the pipeline. So this paper was to estimate acute effects of PM 2.5. So in Delhi, before this paper came out, there were only studies which focused on PM 10 exposure. And so this was the first one to actually estimate effect of PM 2.5 per se. And we the novelty of this work was that we used high resolution 1 kilometer satellite data as the exposure data. And it was daily data. And also we had health like mortality data, which was at daily scale. And then we calculated acute or short-term effects of PM 2.5 and its changes on mortality burden in Delhi. So what we found was about a 0.52% increase in all-cause mortality for every 10% microgram, 10 microgram per meter cube increase in 6 cumulative days of PM 2.5 exposure. And this impact was higher on men than on women. And also one interesting thing was that the impact was twofold higher in winters than in summers. So winters, basically what we could highlight was that in winters, due to the CRB emissions in northern India, that really affects the PM 2.5. It shoots up the PM 2.5 levels in Delhi and surrounding regions. So that is the major impact why this mortality spikes so much in these months, winter months. And then we also did a district, we played around with how we were assigning exposure. So we did it at district level, we did it at pin code level by having information of those who were deceased. So this was kind of a novel work. And then to move into more of policy indicative work, we did, we moved beyond PM 2.5 to using PM 2.5 species. So estimating the impact of species, individual species on all-cause mortality in the same time period. And then we identified a few most toxic species that have the highest impact over and above the total PM, total PM 2.5 mass has on mortality spikes. So these toxic species specifically were nitrates, ammonium nitrates, chromium, ammonium, elemental carbon, and organic carbon. And also, again, males were at higher risk. That's what we found. And also elderly people above 65 years of age were the most vulnerable to mortality effects from maximum species. And again, our work was indicative that a lot of this hazardous risk, mortality risk, is in the winter months, which is because of the CRB emissions and mix of meteorological factors, which do not help much with the dissipation of pollutants, right? And this was an novel work because this kind of study would be helpful in sectoral mitigation and pointing out the specific sectors which are having the maximum health impact, negative health impact. So in terms of climatic factors, I looked into excess mortality due to heat stress. So as I said, heat stress calculated not just out of ambient temperatures, but as a mix of relative humidity, solar radiation, and wind speed. So how the temperature is felt by the human body. So heat stress, we found, was not just a problem on the heat wave days. So in India or in the other LMICs, or maybe even in other countries, heat wave days are more emphasized in terms of having risk for human population. But we found that heat stress, which is a function of not just temperature, but relative humidity, etc., it is also considerably high in non-heat wave days, right? So, and this we tried to assess across climatic zones in India. So we chose 3 different cities in 3 different climatic zones, and we found that the risk was going as high as up to 8.5, 8.1% increase in mortality during the sweltering days. Sweltering days means the highest heat stress days, right? And we also observed a 3 to 6 days lag effect of heat stress on mortality in these 3 cities. Then our work was suggestive of heterogeneity in heat stress impact across diverse climatic zones in India, and we called for developing an early warning system, keeping in mind these regional variations. So one straight jacket heat warning system won't work. So it is across climatic zones, the risk is varying. So it should be kept in mind. And I was supposed to actually present this work, but this is underway and it's still unpublished, but I'll give you an idea. So this was all about, all these 3 papers that I talked about was majorly short-term impact. So I'm also doing a bit of work on long-term impact. So in terms of long-term impact, we are doing some cross-sectional studies, and one of which is where we are looking at the effect of multiple air pollutants and heat and their interplay on early learning outcomes in children aged 7 to 14 years. So what we are trying to do is there's a survey in India which is called the Annual Survey of Education Report, which gives which assesses cognitive scores in maths or arithmetic and reading scores in children in rural India. So we are combining that data with satellite data, and we are trying to see if previous 5 years and the previous 1 year concentration in terms of PM 2.5, in number of heat wave days, all this is affecting the early learning outcomes. And in our initial results, we have found that we are finding that NOx has a higher impact than PM 2.5 on both reading and math outcomes in children. And also heat or ambient heat has a lot more impact than air pollution on learning outcomes. So heat impact, we have found that it goes up to 6% decline in reading and 3% decline in math scores, with each unit increase in days above 90th percentile of temperature. So this is about some long-term impacts, and then I'm also doing a few other health outcomes in terms of long-term impact of PM 2.5 and heat and their interplay, combined impact on those health outcomes like puberty, age, and things like that. And then this is one, as Damaris also talked about, crop residue burning. So it's in her results, she had found that one of the regions, hotspot regions, is India, North India. So this project that I told about, Akash project in Japan, it is working on estimating the impact of crop residue burning on air quality. And in this work that I'm contributing, I'm trying to estimate the health impact of premature deaths due to crop residue burning. In Punjab, Haryana, and Delhi, these three states are the major crop residue burners in the North Indian region. So this is a novel work because most of the existing studies have restricted to improving emission inventories, weighing benefits of various crop management practices, and simulations with timing of burning, how it affects air quality. So, but the health impact studies specific to crop residue burning are very limited, and they have done it at very large scales or pan-India scale, but we are doing it at the hotspot level, which is these three states, and also going up to the district level, which is lowering down the resolution, going fine resolution in estimating the health impact. And this we are doing using the GBD method of estimation, health burden estimation. So our results are, this is just a glimpse of our results, where we find that in these districts which are shaded in dark red, the deaths attributable to PM 2.5 and CRB go as high as up to more than 1,000, 2,500 in a year. So these are annual, and also one bit of this work also looks, one is long-term impact or annual impact of CRB on health burden, and the other is that we are looking into short-term health impacts of spikes in CRB. And then we were able to find using some meta-RRs from published papers that excess risk for every 10 microgram per meter cube increase in CRB component goes up to 20 to 21% increase in daily deaths. Right. So all these works that I'm doing, just wanted to highlight what are the novelty, or how we are contributing in terms of policy impact. So most of this work is specific to India. So, and there is limited or no evidence on multiple air pollutants and synergetic effects of air pollution and climate change in this high vulnerable population. So that way we are contributing. And then it's a purely interdisciplinary approach, because I'm a purely public health person, and then I'm working in collaboration with environmental science people and remote sensing experts who provide the exposure data. And then it's purely data driven, and we are mostly trying to use national level reliable secondary data and satellite derived data. So it's more of a robust analysis, and results are reliable for policy suggestions. And then definitely it has policy implications, because none of this research has been done, or it's in the premature stage. So such works are required to have an evidence-backed insights that can inform policy decisions and mitigation strategies, and also highlight the vulnerable subgroups and regions in India. Then it also gives a holistic understanding in terms of multiple health and development outcomes that we are trying to cover, and see how climate change and different air pollutants impact these health outcomes. So again, just wanted to highlight what are the tangible and intangible outcomes of these kind of works that we are doing. So we are creating these India-specific exposure risk functions for heat stress and air pollution health effects. These are the tangible outcomes in dark blue, and then we are able to quantify health benefits from air pollution and climate change mitigation. And we can highlight the policy makers what areas to focus on. Then all such works, although they are kind of associative studies and they are indicative of association and not causation, but we are giving a direction to more of cohort studies in the same area to have more exact causal inferences of these pollutants and their health impacts. And in terms of intangible outcomes, definitely we are giving policy insights on air pollution and climate change mitigation for human capital development or preservation of human health. Then mass awareness through dissemination of research study results. In terms of policy papers, we are trying and we are writing newspaper articles to simplify our results and just make people aware about such issues. Yeah. Thank you. That was it from my side.
Thank you, Pallavi, for an interesting talk. If we have any questions from the audience, you can either raise your hand or put them in the chat as before. Current, please ask away.
Yeah. Hi, Pallavi. That was a great talk. I like the overview of different projects you've been involved with. Just wanted to understand when we talk of long-term exposure, I understand the link to premature mortality. But you're talking so much about short-term exposure. So I wanted to understand the influence of two confounding factors. One is the amount of or the duration of when a person is actually exposed to this pollution. There are so many studies which say we spend so much of most of the people spend time indoors. And we are talking, when we develop these relationships, we are talking of ambient air quality and relating it to the health data that we have. So do you look into how the time of exposure to this pollutant, because you're talking about short-term exposure, which I'm guessing is a few hours to a few days, right?
Yeah, a few days up to a week or so. So yeah.
Okay, so do you factor in like, is the person being exposed, is it to ambient air quality, or if they're spending time indoors?
So this is one gross estimation that we are making, in that we are using ambient exposures as our exposure function, but it's very difficult to actually get that kind of data of how much time people are spending outside and inside their homes, and these are like big numbers. All deaths that happen in the city of Delhi each day across the different districts or wards. So it's kind of an impossible thing to have for each deceased person how much time they were spending. So these are like gross estimates to give an idea that, and of course we do consider some important confounders such as relative humidity and time, and yeah. So yeah, but there would be
But
limitations.
okay,
as you were
I
saying.
appreciate. Yeah, I just wanted to pick your brains, because I've been thinking on this for a while, and I wasn't very sure if it's easy to tease that, because we're talking about short-term exposure. Long-term, okay, we can say a person goes out daily, is being exposed to a certain concentration continuously for months. Yeah. And the second thing is, because we're talking about short-term exposure, is it possible to say, okay, like most of these, because it's the discussion that air pollution is a cause versus risk, right? So air pollution would probably trigger some health issues that would lead to premature mortality. Now we're talking of these exacerbation of health issues. So are the people who are dying, or probably from the health data, is it possible to say that you were able to establish this because people already had some pre-existing disease? Or can you say that, okay, from the short-term exposure, a person developed? So is this like a new incidence, or is it probably an exacerbation of existing health condition that leads to premature mortality?
I would say both, because these death data that we have would have all kind of people who would be having certain diseases, comorbid conditions. So, and because in India, this death registry data is supposed to have a cause-specific death information, but it's quite fuzzy. So we are not able to tease out exactly what are the causes they are dying of. Otherwise, we could also do a cause-specific study of how PM 2.5 is leading to CVD deaths or things like that. But those kind of data are difficult to have. So we definitely want to do it, but there are challenges in terms of having this health data.
Right. Yes.
Yeah.
No, but this is still impressive work because, yeah, as you mentioned, we focus on so many health studies because the data is available for North America, Europe. So we are limited from the other regions. And I think this is where I think such an seminar by IGAC is important because we want to look at health data in other parts of the world and conduct such more studies.
Definitely. We have, for a few cities, we have been able to manage and collaborate with few other research groups. But yeah, it's definitely remains a challenge, and it's holding us to do a lot more of more insightful studies, as you're saying.
Yeah, because so now you're doing so many studies for, let's say, Delhi. And then the question is that can we even replicate or apply these findings, like you saying, we develop exposure response functions or concentration response functions just for Delhi. Can this be
Yeah.
applied in south of India, where it's a completely different, because we are talking of a different magnitude of PM 2.5. We're talking 200,
Yes.
300 versus below 100 micron per meter cubed. So the impact of that difference in exposure on all-cause mortality or health outcomes is going to be very different.
Yes, but I would want to let you know that there are a few papers now available which are doing multi-city health estimations in terms of short-term impact. So they have been, probably a few groups have been able to catch hold of multiple cities data, so across different regions. As you're saying, South India would be different than North India. So there are now a few papers you may explore, or maybe you can get in touch with me. I can just give you. Yeah. So now we have those kind of meta-analysis kind of thing across multiple cities, how the variations are there in terms of short-term impact.
Okay, great. Yeah, thanks.
Yeah.
Thank you both for an interesting discussion on health studies. Are there any other last-minute questions for Pallavi's talk? Otherwise, I think we will slowly round it off. And thank you, Pallavi. Sibley, do you want to close it, or?
Well, thanks a lot, Damaris and Pallavi, for sharing your work with us. So it's nice to have insights from different places. So we now had an input from UK and another from India. So in case the ones who are watching us would like to present their research, you can nominate yourself or others. The link is on the chat. So please take the opportunity to enjoy this. And it's nice to have this kind of discussions and know what's happening across the world. I also would like to advertise our next skills workshop. So it's going to be with Professor Gao next week, same time as this one. He's going to talk to us about how to write winning proposals. So in case you are interested, maybe you are finishing your PhD, or even like to start your PhD, or would like to get a postdoc or submit for grants. So please check, everything is online. The link is also in the chat. And all of the recordings of the events are available on our website in case you missed something, in case you would like to rewatch. So just check the website. There are always some updates over there and you can have a look. And just take the opportunity that we are sharing all of this information from across the world. Thanks a lot, everyone that joined us this morning, evening, night, afternoon. Hope to see you again next week. If anyone else would like to say something.